Okay, so last time we had learned the basics of PID control, or what was essentially like a proportional component, an integral component, and a derivative component, right? So before we go into further analysis, let's do some problems to build up a case for each of these components. Are they useful? Are they not always useful? Is it sometimes not very wise enough to blindly add a component so that it reduces my steady state error and so on. So we'll slowly build that up with some motivating problems and then go back to analysis of that. Okay, so I start with a simple looking example, which is like a pendulum with no damping, and I'll tell you why this represents a pendulum with no damping. And then you have a controller, and we expect this controller to do a set of things for us, right? So you have a reference input, and then you have the output, you have the disturbance, and the standard feedback configuration, right? So this little block here, if I do the block reduction, this block would just be a series block of the form 1 over s square plus k, right? And this has imaginary roots plus minus square root of k with a j, right? And that response is oscillatory, okay? And the response is always oscillatory, and therefore I call it that it's a system with no damping. And these are the dynamics of a simple pendulum that we did in one of our very first lectures. Okay, so first question which we would like to answer is, what conditions must ds satisfy so that the system can track a ramp reference. Okay, so what should be, are there any specifications on the steady state error? Well, the specification is that it tracks a ramp reference with constant steady state error. Okay. Okay, so first thing we would like to do is to find the transfer function. Right? I'll not spend time on this because we know how to do this now. So this would be d of s over s square plus ds plus k. Sorry, this should be y over r. Okay. And similarly, y of s, or the effect of disturbance on the output, is another transfer function of the form 1 over s square plus d of s plus k. Okay. Now, what does the problem require me to do? Well, it requires me to find what are the conditions on D, if not the exact nature of D, so that the system tracks a ramp with a constant steady state error. This is very similar to what we did while finding out the error constants, right? A type 1 system can track a velocity, a ramp signal with certain steady state error, and so on. We had a little table for that, right? So, okay, so first thing is, what is the error? Error is the reference minus the actual output. So, in this case, the error would simply turn out to be s square plus k over s square plus d of s plus k, right, times r of s. Okay, now for ramp, this would be 1 over s square. Okay, so what do we need? That the steady state error, which is limit s going to 0, s times e of s is this entire guy here, that is s square plus k s square plus d of s plus k times 1 over s square, this thing should be a constant. Okay, which means, well, so this some usual cancellations. So this means that limit. So I put s equal to 0. There is a constant here anyways. So if I just look at this term here, the limit s times s square plus d of s plus k should be a constant. Okay. Now, sorry, limit s going to 0 here. Okay. So, okay, the first guy goes to 0, third guy, well, it should also go to 0 because I cannot change k. Okay, now let us see what it is. So, this means that limit s going to 0, s times d of s should be a constant. So, what should be the nature of d such that s times ds is a constant? Well, ds should be such that it should be some d prime s over s, right, in which cases this cancel out, and then I just take the limit s going to 0, this will be some constant. Okay. So, the condition on d such that these things are satisfied is that d must have a pole at the origin, right. So, this guy must have a pole at the origin. Okay. This answers the first part. Okay. Now, in the second part, for the ds which we obtained in part 1, which has a pole at the origin. Now, for that ds that stabilizes the system, right, find the class of disturbance Wt or Ws that the system can reject with 0 steady state error. Okay. So, I need to find, well, for this ds which had a pole at the origin, I also assume that it stabilizes the system. What are the class of the disturbance signals that I can reject? Okay. So, I will use this guy here, right. So, Ys over Ws is this guy. Okay. So, what I would want is limit s going to 0, s times 1 over s square plus ds plus k. So, this is my Ys, right, or Yss if I would call, that at the steady state there should be no effect of the disturbance on the output, which means the W should not affect this Y at steady state. Okay, and that is only because of W. I am not really considering what is happening with R at the moment. Okay, so this would mean that this is limit s going to 0, s times 1 over s square plus ds plus k, and let me assume that W is of some form s power l, right, could be a step, could be a ramp or a parabolic kind of thing and so on. Okay, so I want this to be 0. Okay, now when is this 0? This happens if and only if limit s going to 0, s l minus 1 d of s is infinity, right. So, why do I say this? Well, look at the denominator here. So, this would cancel out. This would be S L minus 1. This L minus 1 would go here. That term would become 0. K times S L minus 1 would also become 0 when I substitute S to 0. So, for this go to go to infinity, this guy should, sorry, this, for this effect to go to 0, there should be infinity in the denominator, and that is possible when limit s tends to 0, s power L minus 1 ds is infinity. Okay, and this happens when L is equal to 1. Because okay, let us say what happens when L equal to 1. So, when L equal to 1, this guy is S, L is 1 minus 1. What is my ds? ds is d prime of S over S. Okay, so this guy just goes away, and limit s going to 0. I know there is d as a pole at the origin, and this guy goes to infinity. Okay, so in the third part, show that although a PI controller satisfies conditions of part 1 of the problem, it will not yield a stable closed loop system. Okay, so ds is a PI controller, which means it looks something like this: Kp plus some constant Ki over S, or I can just write it as S times Kp plus Ki over S, right. So, this satisfies the condition of the problem 1 that D should have a pole at the origin, and if D has a pole at the origin, then so the condition 1, the part 1 of the problem said find the conditions on D such that the error when the reference is a ramp is a constant. This is satisfied, right? D satisfies the conditions of part A. Okay, now with this D, let us find out what is y of s, or the transfer function of the system. Well, this becomes ds over s square plus d of s plus k. What is my d of s? My d of s is kp plus ki over s here, and again I have in the denominator s square plus kp plus ki over s plus k. Okay, so this would, okay, I just do all the computations. Kps plus ki, here I will have s cube plus s kp plus k plus ki. Okay. Now, is this system stable? How do I find out? I find out by the roots of the characteristic equation or the poles of the system. Now, look at this guy, right. So, s cube plus s kp plus ki times s, sorry, s is already here, plus, sorry, kp plus k plus ki is 0, and I do not even need to see the route table, right, to say that this is always unstable, right, for whatever values of k. You may just want to do it by the route table, but you see that there is no s square term here. The s square term is missing, and as long as that is missing, you will never have a closed loop system that is stable. As a little exercise, you can just convince yourself by drawing the route table. So, the conclusion here is that although D of S satisfies the conditions of problem number 1 with a PI controller or which has a pole at the origin, it leads to a closed loop system which is unstable. And therefore, even though a PI controller has the effect of reducing the steady state error, if this was not true in problem number 1, this would never be able to track a ramp, right. So, by putting a pole at the origin, I see that well I track the ramp, but with some error, right, but then the closed loop turns to be unstable. So, these are little things which we need to be careful while we design PI controllers or use them blindly. So, the conclusion is, even though this theoretically satisfies, it will be meaningless because my system is unstable. So, this saying that DS has a pole at the origin means nothing because the system is unstable. For any of this analysis, you need the closed loop system first to be stable. It is not stable, therefore, this is not true. It could be true for some other DS which has a pole here, and it could be some S plus 1 over S plus 2, that could be true, that could lead to a stable DS, right. And here I am not really talking of a stabilizing DS, right, I am just saying condition 1. The second part of the problem assumed DS to be stabilizing. If DS was not stabilizing there, I do not really need to care about disturbances also, right. Only assumption in the second part was D has a pole at the origin and it has a stabilizing effect. So, you see that just adding a Kp plus Ki by S or a PI control does not have a stabilizing effect in this case, and it could turn out that in many higher order cases this could be true. So, we need to be careful before looking at the problem statement of improving the steady state performance through a PI controller is always comes with a bit of warning that you should look at the closed loop system to be stable. Okay, the next is, now part 3 told me that PI was not a very wise decision or a very wise choice. Now, can I use a PID control? Okay. So, a general structure of the PID control would be, okay, you have Kp, the proportional term, the integral term and the derivative term, in which case my closed loop transfer function Ys over Rs becomes, okay, I will just skip the computations, I will just write down the end result, Kd S square Kps plus Ki over S cube plus Kd S square plus Kp plus Ks plus Ki. Okay. So, this gives me a little bit of hope because there the S square term is not 0, okay, and ds still has a pole at the origin. Okay. So, the part 1 is satisfied. Now, let us see what happens with this one. So, I can just draw the route table. I have S cube terms as 1 Kp plus K, S square terms Kd and Ki. Then I could compute the S1 terms accordingly as Kd Kp plus K minus Ki over Kd and a 0 here, and S power 0 would simply be Ki. Okay. Now, this is positive, this is positive, this is positive, and I can choose my Kp and Kd such that this is true. So, just find out, right. So, this is stable for Kd greater than 0 and Ki greater than 0, right. Of course, Kp is always greater than 0. right. So, this is very, very straightforward to find out. Right? So, Ki should be greater than 0, Kd should be greater than 0. If these two are true, you plug it in here and you will find this also to be greater than 0, right. So, this the additional condition we need to impose is Kd, Kp plus K is greater than Ki, right, for the system to be stable. Right. The second one would mean Kd should be greater than 0, Ki should be greater than 0, and this is the third one. Okay. So, as said earlier, so this guy has an effect on the steady state performance of the system, and the derivative component has an effect on the transient performance of the system, right. Okay. So, this is a very basic illustration of when to use PI, when to use PID. Again, not a very general answer, these are just a special case of it, right, of why we should be careful while we are using PI controllers. Okay, we will see a little more different types of problems. Okay, in the second problem, well, it's a very simple model of automobile speed control using a PI control. Well, there is a disturbance also, right. So, and we will see what all we could do with this, right. So, first, how to say, part A we will do is with zero reference velocity input, which means this guy Vc is 0, find the transfer function relating the output speed. Okay, let me call this V, relating the output speed V to the wind disturbance W here. Okay, well, okay, this is not really a big deal. Vs over Ws, assuming V to be 0, I can easily compute this as Ms over I have S square plus M K3S plus M K1 K2. Okay. So, this is straightforward, I will not go into the details of doing that. Okay. The second part, okay, what is the steady state response of V if W is a unit ramp? Again, still keeping Vc to be equal to 0. So, well, typical formula Vss is limit S going to 0 S times V of S. What is V of S? This is Ms over S square plus M K3S plus M K1 K2 over or multiplied by 1 over S square. Okay, so this will turn out to be, so this will go away. I am just left with 1 over K1 K2. Okay. Third part. What is the type of this system with respect to some reference signals? Okay, so we look at it in terms of E is Vc minus V is 1 minus and usual the way we compute the steady state error is through the final value theorem, limit s going to 0 s times E of s. Okay, so here the position error, okay, I'll skip the computations, s tending to 0, g of s is infinity. So, the steady state error with a step input is 0, right. Similarly, kV turns out to be k1, k2 over k3, or ESS with a ramp is k3 over k1 k2, right, which means it's just a type 1 system, right, that could be easily computed. Okay, so in the third and the last problem, we deal with again a very simple model of a satellite attitude control. So, with J being the moment of inertia, so you have a certain reference attitude and then you have the actual theta, right. Okay, so and then as usual W is my disturbance torque. Okay, in the first part, with a proportional controller, we slowly see the effects of P, PI, PD, PID and see what they mean with respect to reference tracking and even disturbance rejection. So, first thing is to start with the proportional controller, which means my ds is simply a constant Kp. Can I stabilize the system, right? So, can I stabilize? Okay, so let's say, okay, so for some of these purposes, I would sometimes assume that this H r and H y are equal to 1, even though nothing will change, even if they are non-unity. Okay, so when ds is just Kp, then my characteristic equation is 1 over d Js square, assuming this to be true, which means 1 plus Kp over Js square is 0, or S is plus minus square root Kp over J. Yes, with a, since this will be in the imaginary axis, as Kp and J are always greater than 0. Okay, so this system will always have poles, no matter whatever I do with the Kp, the poles will just lie on the imaginary axis, right, and so therefore the system is not stable. At best it can be called as marginally stable. So, So, with just a proportional controller I cannot stabilize the system, right. That is the first thing. Okay. What could I do now with a PD controller? Okay. In that case, well, the transfer function theta over theta r of s is Kp plus Kds over Js square plus Kp plus Kd times s. Okay. Now, you look at it. So, earlier we just had roots which were imaginary. So, we just had this term Js square plus Kp. Now, I have this additional term Kd which introduces damping to the system, and this is second order system with all constants being greater than 0. I know that this system is actually stable now, and by appropriate choice of Kd and Kp I can play around with the peak overshoot or the settling time, the rise time and so on. Okay. So, first thing, with a proportional controller I could not stabilize the system, I could just move the roots of the system along the imaginary axis. I put a derivative term, I add damping to the system, right. In the first case we just ds being a proportional controller, I did not have this damping term. This term corresponds to 2 zeta omega n, which means zeta equal to 0 if Kd is equal to 0. There is no damping, so the system will always be oscillatory. In the second case, I introduce a damping and stabilize the system. Okay. So, if my reference is 1 over s, what is the steady state error? Okay. So, for this I will just use some constants to compute these values. That J is 10, since it is in the moment of inertia thing, so it will be Newton meter second square per radians, then Hy Hr is equal to 1. Okay. So, when I just use that theta r is equal to 1 or theta r of s is 1 over s, then when Hr equal to Hy, the steady state error is 0. I will leave that as an exercise to you, because you can see lots of things happening here, right. You have, well, if I just consider this, I have 2 poles at the origin. Okay. So, therefore, I can easily track a step signal. Okay. Third case, what is steady state error with disturbance inputs? Well, for that I need to find out what is the transfer function theta s over ws, or the effect of w on theta, that I could compute. Again, this is a straightforward computation, Kp plus Kds times Hy, right. And then, well, if the disturbance is 1 over s, then theta ss, or the steady state value of theta with w being equal to s, is minus 1 over Kp times Hy. Okay. So, this kind of controller does not eliminate disturbances of this form. It will get more complex when you have s square and s cube and so on. Okay. So, what do we observe from here, right? So, again go back to the plant. The plant has 2 poles at the origin, and these 2 poles were okay to eliminate the steady state error when I was tracking a step reference. But these guys are not useful enough to reject disturbances. That is seen from here, and therefore, a pole at the origin helps in the reference tracking. But if I were to reduce the effect of disturbances, I may need an integral component here, or a pole at the origin for the controller. Okay, so in the next part, we will just see what happens when I use a PI kind of controller. Okay, so what does this controller do? And this again not very different than what we did earlier, right? So in this, with PI control, the characteristic equation becomes Js cube plus Kp of S plus Ki equal to 0. This is again assuming this to be true. Okay. Now this is unstable, right? I don't really need to analyze this any further. Okay. So this with the PI controller I know is unstable. Now it doesn't really help me to compute the steady state error anymore, because whatever I do, the system is unstable. Therefore, just by doing a PI control and then doing the steady state analysis is really meaningless, right? So first we always have to check for stability before we do any other analysis, even though the math of that ESS is limit S going to 0 S times ES will give me a number, but this was valid only if this is a valid transfer function or ES is a stable signal. If this is unstable, then nothing can be done, right? So this we even did while we were discussing about the final value theorem, right? The system must be stable so as to apply the final value theorem, right? So that we need to be careful of all the time. So similarly, we could also do the effect of disturbances, right? So the effect of this I will leave as an exercise. Effect of disturbance with a PI control. Okay, just check this. Will the, well, I just use the word closed loop even though it is not the actual closed loop. The closed loop with respect to W stable now with a PI control, right? Just try to solve this. This should be, once you know this should be very obvious. Okay, so the last part now is to check again what happens with a PID control. So PID control, again I will have Kp plus Kd times S plus Ki over S. I'll skip all the steps, and you just have the transfer function of the form Js cube plus Kd S square plus Kp times S plus Ki equal to 0. So similar to what we had in one of our earlier examples, right? And now I can really find out conditions under which the closed loop system is stable, right? Now again, I'll just leave this for you as an exercise. So analyze the steady state error for different inputs. Maybe for a step and just for a ramp, right? So I'll just leave this as an exercise because it's just a very manual thing. So what we have learned, right, just to summarize, is we need to be careful when we are adding an integral control. It might seem a little misleading that it will improve my steady state performance, but it might lead to an unstable closed loop system, right? And then of course when I use this PID, well, I just have to then I should choose the constants Kp, Ki and Kd such that the closed loop system is stable. This can come from the Rouse table, right? This we are now very well familiar of how to analyze stability of this, right? So what we will do next is to take this as a bit of a background and analyze these kind of things a little more can I directly do this practically? Are there any difficulties, right? So, can we relate to what we learned in terms of the root locus plots? Can we relate these things to what we learned in terms of the Nyquist or the Bode plots? Do these guys talk anything about relative stability? At the moment we just haven't talked anything about relative stability, right? So, all those things we will analyze once we have understood what adding of these controllers mean. Are they good? Are they bad? Are they sometimes good and sometimes bad? Okay, thank you.